Yeah, thank you very much. And thank you very much also for the organizers inviting me to this conference. Yesterday, I already had a short hike in the city. I must say it's very beautiful. So I'm very happy to be here also because of that. So today I thought I make a talk that is a little bit different. So I will talk about some challenges that we usually have in free space quantum communication, and especially also looking at the interesting interplay between technical challenges and foundational questions that come along. So right now there's a lot of happening concerning quantum technology and a lot of investments in there. And it's always interesting to see where the challenges really lie and what we can learn from that also for more fundamental experiments in the future. So if we talk about all those technology being developed, of course, you can look at quantum computing using superposition states, entanglement, and so on. But also, of course, quantum communication. And quantum communication, of course, can also come at different sorts. So, of course, you want to connect quantum information processing units, maybe, or you want to do quantum cryptography. That means you look at security and you want to generate secret keys. Now, in common with quantum communication protocols is always that usually they are done with light. And there's a good reason for that because of black body background and black body radiation. Because, I mean, of course, you can also think about microwave radiation, but then it is usually very, very hard to achieve a regime where you can transmit quantum states so that they are not disturbed. Unless you use fridges where you can, of course, do this also in the context of quantum computing, and there it is done. Now, if you think about light or infrared light, I would say that is still what we can do and what we know a lot, for example, in classical communication systems. So, of course, one thinks about optical fiber system, and that is fine. A lot of quantum communication is done in optical fiber systems. There is pro and cons. Of course, it guides light very, very nicely. On the other hand, usually there's also scattering in optical fibers. You have absorption. The absorption scales exponentially. So you have to take that into account. When you have different channels at the same time in one optical fibers, for example, at different wavelengths, there might be cross-coupling. There might be nonlinearity that is happening. On the other hand, if you take free space channels, you're a bit more free when taking into account those things. And also, of course, you're much more free into reaching different users or making the experiment also work on places where there are no optical fibers. And what I will do now is I will look at different examples with increasing complexity. So look at examples of free space channels from building to building, small free space channels. I will have a look at free space channels from mobile platforms, for example, airplanes, and then go to a bit more extreme cases, and that is satellite quantum communication. Now, if you look at a typical free space channel that you have from maybe a building to some platform or something like that, then of course there's the obvious culprits that things might go wrong. You have turbulence, of course, in the atmosphere. That is just temperature fluctuations, changes the refractive index. That is generating different challenges. So one is a very easy challenge that is your beam gets distorted, so you have to cope with these distortions. Even in classical communication systems in free space, of course, people know how to use adaptive optics that can play with the wavefronts. We just saw on the talks before that you can generate very, very interesting modes with that, but you can also correct, of course, with those kind of technologies. Then, of course, turbulence also generates beam deflections. So you're not really pointing where you want to point. So you have to also cope with that. And then, of course, in realistic links, there's also weather. It can rain, it can snow, and there are clouds. Clouds are really bad. So with clouds, actually, the absorption is really dramatic. However, sometimes it's surprising how well some free space channels still work. So, for example, if you have light rain is perfect. Actually, sunny days are very complicated because sunny days means you have a lot of turbulence, right? So it's much better to have a dull, gray, light rain day. That is good for quantum communication. Now, There's one example here from some realistic channel over some afternoon. And you see, I mean, of course, there's some transmission changing. You also see one very bad situation that actually was a hailstorm going through, so this can happen. So these are the obvious things that are there. Now, how to deal with these a bit more complicated situations like all those disturbances? Well, you can also look at how to encode the quantum states. For example, you can go to something like a decoherence-free subspace if you want to have a fancy word for it, or you use some encoding that doesn't suffer so much from those disturbances. For example, you can use polarization because polarization actually survives quite well in free space, and that's because usually if you have the atmospheric channel, there's nothing that is birefringent. Exception, if you have snowflakes, that's pretty bad. That is also what we realized. Now, in Erlangen, we studied this for quite some while in the continuous variable quantum optics regime. And you can then show that polarization is so stable that you can even transmit squeezed states over such a fluctuating channel, and you can make a Wigner function tomography of the squeezed states, and that still works because polarization is so stable. Now, lately, we looked at some different settings. For example, if you want to put up some ad hoc link, and we did this in the city of Jena with some colleagues from Fraunhofer IOF in Jena, and you have some link, and you want to generate a secret key with quantum key distribution, then of course you have to take into account all those different challenges of the fluctuating channels. And especially in the regime of quantum key distribution, that is critical. Because basically, how does quantum key distribution work? I mean, we transmit quantum states in one sort or the other in some sort of encoding, then we measure, and then we do statistics, right? And from that statistics, we bound all the information that an eavesdropper can have. Now, doing statistics on a fluctuating channel is, of course, not so easy. So we have to take into account all of that. Now, especially with continuous variables quantum key distribution, if you want to do the encoding in a realistic setting, that means you encode in phase space in a discrete way. For a long time, people had struggled with theoretical security proofs that are able to cope with that infinite dimensional Hilbert space. So luckily, this changed lately, and especially we collaborated with the group of Norbert Lütgenhaus, who made a security proof that can cope with all of those considerations. And we combined it with techniques we developed together with Ladusenko some while ago, which can actually cope with those fluctuating channels. And so in this city of Jena, we did some measurements along these lines, and you can see on the left side the transmission histogram. So actually, we really have this fluctuating channel. And the trick there is basically you bin your channel into stable transmission channels. So that's kind of your virtual channels you work with, and you do all the statistics and the analysis of the quantum states on those virtual channels, on those bin channels. And then if you do that and you do enough measurements, then actually to much of our surprise, the numbers were good enough that if you measure long enough for your statistics, then you would be even able to generate a key with those very demanding new security proofs. And I say very demanding because those kind of new security proofs use a kind of hypothesis testing, and it is not so trivial to actually achieve that hypothesis testing to generate a secret key. So that is work done mainly by my colleague Kevin Jaksch in Jena. And you can see one advantage of continuous variable quantum key distribution in that case is that these sort of continuous variable measurement, that means homodyne or heterodyne measurement, it's a beating measurement, it's interference. So it is a perfect filter for all the stray light that you usually have in atmospheric settings. And that is, of course, very, very good to cope with that challenge of stray light that you usually have and that might saturate the clicks in your measurement devices. Now, if you go a bit further and you have some mobile platforms, then the next challenge you might think about is using an airplane. And that is what we are currently doing in one of our bigger experiments in the German QNet project. So there we have several key experiments that we are looking into. And one of them is how to cope with mobile platforms, for example, an airplane. And so currently we have several measurement runs where some airplane starts in Munich. That's the research airplane from the German aerospace, the DLR, and it does half circles around the Max Planck Institute in Erlangen, and it transmits quantum states down to the institute in Erlangen. Now, of course, the first challenge here is to really transmit the light at all, right? Because I mean, you have an airplane, it's flying, it's 10-kilometer distance, there's a lot of fluctuations and so on. So this is something we left to our classical experts from DLR and Fraunhofer IOF. So they worked at all the adaptive optics and so on, and this has to work, right? Then this is not completely decoupled from your quantum optics experiment, because all this way you transmit your quantum states, that actually defines your mode structure and that defines your quantum state. So you really have to be careful not to mess up the definition of your quantum state while doing these things. Now, what we looked at first, we had actually one of those continuous rubble quantum communication channels, but this time we didn't use polarization encoding to transmit the quantum states, but we just used phase space encoding, so amplitude and phase modulation. And usually, of course, that gets scrambled because of all the phase scrambling that you have in the atmosphere. However, what we did here is that we transmitted those quantum states with repetition rates and with frequencies that are very high. And so basically, the atmospheric channel is more or less static when we transmit those quantum states. And then we can apply all sorts of tricks that we learned from engineering for coherent optical communication. And with that, you can actually recover your quantum states. And this is one of the cases where digital signal processing on quantum states is okay. So you can, in retrospect, really fix a lot of those impacts of the fluctuating channel by digital signal processing, by special filtering operation and so on. You only have to be very careful that with that processing, the definition of the quantum state is really the definition that you actually used in your encoding. So you have to really make this compatible. And again, actually, to our surprise, the quality of the quantum states that we could recover were quite good. So you can see here some examples of 4 coherent states in phase space, and also 16 coherent states encoded in phase space. And you see they're a bit elongated, and that's actually because you still have the fluctuations in there. So that would be the next step then to do the binning according to the transmission, the classical transmission of the channel. And that is work that has been mainly done by Stefan Richter. Now, another experiment we looked at is how to actually, how easy is it to couple basically a flying qubit to a stationary qubit? And that is not so trivial because of all those fluctuations, of all those phase shifts, and also because of Doppler shift, because you really have to hit the transition. And what we did there is we had one source of single photons, a down conversion source, on the plane, and there's the ion trap of Gerd Leukes at the Max Planck Institute, and we tried to couple that on the transition of an ion trap. So that experiment is still ongoing, and in autumn we have another flight campaign. But I can already tell you that we saw first coupling of a detuned coherent laser, so coherent states, to that ionic transition coming from the airplane, right? Which is not trivial because you really have to hit the right wavelength on that plane. And you can learn more about that at the poster of my colleague Sheng tomorrow. Now, if we go a bit more extreme, then you go longer in distances and you go to satellite communication. And the reason for that is that if you want to go through optical fiber systems, the losses are exponential, and exponential scaling is always bad. Now, if you do the detour through satellites, you still have loss, but that loss stems from diffraction because the aperture is limited. That scales quadratically. So that is, of course, better than exponential. And this is why people looked into that. There was this very nice mission Meteus from our Chinese colleagues, and they also have a new version now with a smaller, more compact satellite to show that in principle, all those concepts work, and we can actually transmit quantum states, receive quantum states, and also generate, for example, secret keys with quantum key distribution. There's different efforts to look at that with different concepts. You can have quantum states sending from space down to ground. You can send them up. And there's always pro and cons how you do it. For example, if you want to optimize a secret key rate and key distribution, you better send down quantum states from space down to ground. And the reason for that is that in space, of course, you've got vacuum, there is no fluctuations. And it's always better to have no fluctuations at the center, because then the pointing errors and the fluctuations are not so bad. On the other hand, if you want to be flexible with quantum sources, trying things with quantum sources, then of course it's much more convenient to have the source on ground, because you can exchange the source easily. And what one learns when one dealing with those things is that space engineering is very, very hard. So you don't want to change things in space. So keep space simple and put complexity to ground. Now, in Europe, there actually had been quite some effort in classical space laser communication for decades. Actually, the only 24/7 running laser communication link in space is operated by the European Agency for the Sentinel satellites of the European Commission. And some while ago, we did some measurements actually on one of those geostationary satellites transmitting laser light down to ground, operated by the company TESAT Spacecom. And what we could show that actually on ground, those states are very much quantum noise limited. And this not only has some technical message, but it also is important to look into ways, I believe, to do measurements in quantum mechanics in extreme cases. I don't believe that anything strange would popping out in those kind of measurements because of quantum gravity or so on, right? Because we just do quantum states propagating on a kind of background. However, one always has to do this in extreme cases and look at bounds, because even the national security agencies ask questions. For example, can there be influence of quantum and gravity, and might that be an influence on those technology? Okay, so if you now go further and go a bit more extreme, there's satellite-based quantum key distribution, and in Europe, there's the mission Eagle-1 from the EU and European Space Agency, where we are the scientific lead. And that mission is really to generate a secret key with quantum key distribution. And I will show you a little bit kind of what you have to design for those kind of missions and where the challenges are. And they are mostly not where you expect them to are, when you're really forced to build the entire system and not only do a proof of principle experiment. Now, first you start with questions like, okay, which scheme do you want to take? Do you want to take continuous variable field measurements? Do you want to take discrete variables? Now, when you look at the protocols and real-world numbers, then you find out that actually only discrete variables will work in a realistic setting without further assumptions. And that's because in discrete variable, there's kind of a post-selection already happening. When you detect a photon with your single photon detector, you already kind of select all the other cases when you lose part of your quantum state. Whereas when you do field measurements, you always get a value. Yeah? And you have to do a lot of error correction to cope with that. And that actually helps in DV protocols for loss. Then you can think about taking a true single photon source, decoy protocols. Now, if you look at that, decoy state protocols just use coherent states, and you can send them with gigahertz rates. and you will have tremendous loss in those extreme cases. So it's much simpler to use coherent states with gigahertz rates right now than the true single photon sources. I'm more than happy when they come up true single photon sources with gigahertz repetition rate. Phase versus polarization, choice of degree of freedom. Usually people looked at polarization because of the obvious reasons. It's very stable. However, when we looked at that, we saw that you want to put complexity from space to ground. And so phase encoding is very well known in classical communication. So people know how to do that. The space engineers know how to do that. On ground, you need an interferometer, but on ground, we know how to optimize systems. In addition, when you want to put your quantum states into a fiber network on the ground, it's much easier to use phase encoding. So at the end, it's really, we opted for phase encoding because that's much more compatible also with the telecom communication technology that is there and can be used. Then you can look at further active versus passive basis choice and so on, 1500 nanometer versus 800 nanometers. Again, you might be thinking, okay, 800 nanometers is much better because it can focus better your diffracted beam. However, then if you talk to experts, it's not really that much an advantage because there's, of course, aberrations in optics. It's much harder if you go to space optics and so on. And another very important point, background. So background light is much less at 1500 nanometers. So this you have to take into account, and it all comes in a nonlinear formula of your key rate. So we ended up with some satellite quantum key distribution protocol, and I want to highlight Kevin Güntner that worked a lot on that, that is working around that and using a BB84 decoy protocol with relative phase encoding in the telecom band. And that is, as we found, the most optimal solution for these kind of things. And you can read more about that in an Eagle One protocol workshop website from the company SES. Now, I don't want to go into the details here. The challenges there are, of course, that you have to lock interferometers on ground because of all the Doppler effects, and it's extreme Doppler effects in those fast-moving satellites. But you can do this. You can do this when you have some classical reference pulses where you lock your interferometer. Now, again, here you might naively think, well, I take very, very bright classical states and I do that and everything is fine. But then you find out that actually the dynamic range on space hardware is limited. So actually, what comes down at your ground station is only single photon clicks. So you have to lock an interferometer in real time on single photon clicks. And so we had to work out a way how to do this in an optimal way in real time. And basically the trick is actually the simplest way you can look at. So you always change the phase of your interferometer depending on whether you have a click in one or the other arm of the interferometer. That turned out to be optimal. Now, there's a lot of encoding problems. I won't go into details now. Maybe let me just say one aspect is clock recovery, and Konrad Rösler was investigating that a lot. Doppler shift is extreme, and also chirp is extreme. It's not only changing the wavelength, but the worst culprit is actually the chirp in the time base, because you are losing the time base of your quantum states very, very quickly. So if you look at that, you have a significant effect on the time base. Now you have to cope with that in real time. And then, of course, we have already those reference pulses, so we can actually also use them for recovering timing information. We have gigahertz rates, though, again, we only have single photon clicks. So you have to cope with the difficulties how to do this on single photon clicks. So forget about Fourier transform to find out your timing reference. This doesn't work on those kind of when you're in this staffed regime, when you only have very, very few clicks. So we stole some ideas from our astronomy friends because they have similar problems. And there's the technique of epoch folding, and that is very, very efficient to find out timing information and time periods with very sparse data. Now, again, that's not enough because you have to find out your absolute timing. So you want to have absolute timing on 10, 20 picosecond. And so you add some frame number decoding, and we learned a lot from navigation systems, satellite navigation, Galileo, GPS. So we put in some pseudonumber sequences for autocorrelation functions, and again, only on single photon clicks. And in addition, you have to encode your frame number, and you know that you have a lot of loss. And that's basically pulse position modulation that we do. And we know that this is optimal in the photon-starved regime in quantum mechanics. And so we can achieve absolute synchronization with those very, very few photon pulses. So that's kind of the challenges you have with realistic system, and many of them then give you feedback into fundamental questions, how to do optimized measurements with quantum mechanics. Now, that is kind of a big satellite system we worked with. You can also do this very, very much smaller and integrated. And here we have another mission where we build a small CubeSat that is a 30 centimeter big CubeSat with highly integrated devices. For example, we put in sender modules for coherent states that use photonic integrated devices. We have quantum random number generators. And that's, of course, yet another challenge, how to build all those systems such that they are so small, use very, very few power and power consumptions that you can actually put this up into space. That satellite had been built some years ago, already was waiting for launch, and Jonas Budelko, Joost Vermeer, and Ömer Bayraktar worked a lot to do that. And that's actually, I would say, one of the few exceptions where you can build parts of the satellite and still kind of measure it in your PhD thesis, because that's only possible in CubeSats. Otherwise, that won't work. So that was launched last year with SpaceX, and is now in an orbit of about 500 kilometers. And we just had the first flight a few weeks ago after testing all the electronics. And we are starting to measure with the devices on board, and will transmit the quantum states. So next year, we will build a bit bigger satellite that then is able to do full quantum key distribution with this kind of CubeSat technology. And then, of course, we can play around even more with all those aspects. So just to sum up and conclude, so I think just specializing on the free space aspects, that is a very active field of development. We saw there's a lot of challenges. Some of them seem to be quite technical, but then you find out in order to solve them, you actually have to go back to quantum physics and solve some problems there. So it's quite interesting to have this feedback between technology challenges and fundamental physics that you have there. And again, there's some other proposals, of course, to do some other interesting ideas, testing in space that one can go into. And with that, I want to thank my group for their fantastic work, and also you for listening. Thank you.
Have you heard my question?
Say this again, please.
Yeah. So can you tell us what is the diameter of your telescope on the ground in those quantum key distribution experiments?
Yes. So the diameter that we're using in our reference station is about 70 centimeters. In space, it's not very big. It's about 8 centimeters in space. And this is some parameters you can, of course, play with, right? And at the end, you can say it's just money, right, that you need and that you need to optimize. However, there's also, of course, fundamental problems or challenges because, of course, if you grow the diameter of your apertures, then at the end you want to have adaptive optics to be really able to cope with all the light. And if you grow that, it gets harder and harder to have efficient adaptive optics. So there's a sweet spot in how to design all those parameters.
Thank you for your talk. I want to ask about the squeeze states with discrete modulation. So, are there any specific downsides or like penalties for using that theory with squeeze states that comparing to the coherent states with discrete modulation? Are there any maybe additional drawbacks because of the asymmetry of or some other assumptions that cannot be employed?
Yeah. No, thank you for that question. So I didn't really go into detail there. So the quantum key distribution experiment we did with that security proof was with coherent states. You can also do it with squeeze states, and for some certain parameter regimes, it might be beneficial to use squeeze states. Um, However, of course, there are some technical challenges again here, or technical quantum mechanical challenges. For example, you have to make sure that you align really your basis with that of the squeezing and anti-squeezing. So if this walks off, then of course quickly you go into a regime where you suffer under the anti-squeezing. So we saw this nice talk about the spin squeezing. Actually, same mathematics, same problems in that sense, very, very similar. And here also, and here, that is one of the cases where polarization encoding helps, because with polarization encoding, you can make sure that the alignment in phase space, which is then polarization space, is rather stable.